Hello there, and welcome to the Sleepy Science Channel. Tonight, we are going somewhere few human beings have ever been. Not far in the way that distances on Earth feel far, not across an ocean or over a mountain range, but straight up, quietly, through the thinning layers of our atmosphere, past the last soft breath of breathable air, and into the hushed and infinite dark of space. And up there, floating in orbit around our blue world, we are going to visit something extraordinary. A place that orbits the Earth at a speed that would take your breath away if you stopped to think about it, and yet somehow, in its own strange way, has become one of the most ordinary places in the universe. A home, not built on the ground, not anchored to rock or soil, but assembled piece by piece among the stars, by human hands, over the course of more than a decade. Tonight, we are going to explore the International Space Station, and we are going to do it gently, at a pace that is easy and unhurried, the way a warm current carries you without any effort at all. There are no tests here, no urgency, nothing you need to remember or hold on to. All you need to do is settle in. Let your body grow heavy and still, and allow the quiet wonder of what humanity has built up there to carry you softly toward rest. If you have found your way here and you are enjoying these slow and peaceful explorations of the world around us and beyond it, I would love for you to like and subscribe, or leave a gentle thought down in the comments below. It helps others find their way to this quiet corner, one sleepy soul at a time. But for now, the stars are waiting. Let us begin. The International Space Station is the largest structure humans have ever placed in space. When you picture something built in space, you might imagine something small and contained. A capsule, a pod, something that fits neatly inside a rocket and gets carried up all at once. But the International Space Station is nothing like that. It is enormous, stretching roughly 109 meters from one end to the other. It is wider than an American football field. Its solar array wingspan is even greater than that, extending out like a pair of vast and gleaming wings catching sunlight above the curve of the Earth. If you were somehow able to place it gently on the ground in a city, it would cover most of a city block and rise several stories into the air. It weighs approximately 420,000 kilograms. Not that weight means what it usually does up there, because in orbit, everything is in a state of continuous freefall, and that immense structure floats as lightly as a bubble, but the mass of it, the sheer accumulated material that had to be lifted out of Earth's gravity and assembled piece by piece in the void, is almost difficult to comprehend. It was not built all at once. It could not have been. The station is made up of more than 100 individual components. And those components were delivered over more than 13 years of assembly missions. The first module was launched in 1998. The final major components were added more than a decade later. In between, astronauts went outside on spacewalks that sometimes lasted 8 hours or more, fitting pieces together in the vacuum of space, turning bolts with gloved hands, connecting cables in the dark, building something that human beings now call home. The station orbits the Earth at roughly 400 kilometers above the surface. That number, 400 kilometers, sounds large, and it is. But in the grand scale of space, it is almost nothing. The Moon is roughly 384,000 kilometers away. The Sun is 150 million kilometers away. In comparison, the International Space Station hovers just barely above the outermost wisps of our atmosphere, in a region called low Earth orbit. It is close enough that from the station's windows, you can clearly see the continents below. You can watch weather systems moving across the ocean. On a clear night, you can see the lights of cities scattered across the dark side of the planet, like fallen constellations. And yet even at 400 kilometers up, the environment is completely and utterly alien. There is no breathable air. The temperature in direct sunlight can reach over 120 degrees Celsius, and in the shadow of the Earth, it plunges to nearly minus 100 degrees. The radiation environment is intense, constantly bathing everything in charged particles from the Sun and from distant cosmic sources. Without the protection of the Earth's atmosphere below, life as we know it would be impossible. The station is a bubble of Earth conditions sustained by extraordinary engineering, floating just barely beyond the boundary of the world that made it. The station travels at approximately 7.7 kilometers per second. Let that settle in for a moment. 7.7 kilometers every second. That is roughly 28,000 kilometers per hour. At that speed, the International Space Station completes one full orbit around the Earth in approximately 90 minutes. In a single day, the crew on board orbits our entire planet 16 times. They watch 16 sunrises and 16 sunsets every 24 hours. The sun appears to rise in the west and set in the east because the station is moving faster than the Earth rotates beneath it. There is something deeply peaceful about imagining that. 16 sunrises, 16 moments where orange and gold light floods through the cupola windows and washes over whoever happens to be floating there, watching. 16 times a day, the slow and ancient ritual of dawn begins again. And 16 times, the golden light fades into the soft bruise of sunset, and then into the pure black velvet of night, scattered with stars. The station moves so fast that it only takes about 10 minutes to cross the entire width of the continental United States. It passes over most inhabited places on Earth at least once a day. If you know when to look and where in the sky to look, you can see it from your backyard. On a clear evening, a bright and steady point of light moving silently and quickly across the stars. It does not flicker like a star. It does not blink like an aircraft. It simply moves smoothly and purposefully, a small bright dot of human ingenuity crossing the darkness. The station has been continuously inhabited since the 2nd of November in the year 2000. This is one of those facts that is worth sitting with. Since the 2nd of November in the year 2000, there have been human beings living in space without interruption. Through every season, through every year that has passed since then, through everything that has happened on the surface of the planet below, a small group of people has been up there, floating above the clouds, living and working and sleeping in a place that no human being had ever occupied before. At the time of writing, that continuous habitation has stretched to more than 24 years. More than 24 years of uninterrupted human presence beyond the surface of the Earth. The first crew to arrive was called Expedition 1, and it consisted of 3 people, an American commander named William Shepard, and 2 Russian cosmonauts named Yuri Gidzenko and Sergei Krikalev. They arrived aboard a Russian Soyuz spacecraft and floated through the hatch into the newly assembled station, and they began what has become the longest unbroken period of human habitation in space in history. Since that day, more than 270 people from more than 20 countries have visited the station. Scientists, engineers, pilots, doctors, teachers. People from places as far apart as Japan and Canada and Germany and Brazil and the United States and Russia and beyond. All of them spending time in this small, extraordinary place above the world. The station is a collaboration between 5 space agencies. It would be impossible to tell the story of the International Space Station without talking about how it came to exist. Because it did not come from any one country or any one vision. It emerged from something rarer and perhaps more meaningful than that. It emerged from cooperation. The 5 agencies that built and operate the station are NASA from the United States, Roscosmos from Russia, the European Space Agency, the Japan Aerospace Exploration Agency, known as JAXA, and the Canadian Space Agency. Each of these organizations contributed modules, systems, hardware, and human expertise. Each brought something unique. And together they assembled something that none of them could have built alone. The Russian segment includes the oldest parts of the station, including the very first module ever launched. The American segment is the largest portion and includes the main laboratory facilities. The European and Japanese segments each contain dedicated science laboratories of their own. The Canadian contribution, including the remarkable robotic arm system that has become one of the station's most essential tools, winds through the whole structure like a mechanical backbone. There are moments in history when you can look at something and see the best of what human beings are capable of. Not the conflicts or the competitions or the fears, but the extraordinary things that happen when people from different places, speaking different languages, trained in different traditions, choose to work together towards something larger than any of them. The International Space Station is one of those things. The station has a living volume roughly equal to a 6-bedroom house. This surprises most people who imagine space stations as cramped and claustrophobic. The pressurized volume inside the International Space Station is approximately 931 cubic meters, spread across all the connected modules and tunnels and labs that gives the crew a reasonable amount of space to live and work in, roughly comparable to a large family home, though of course the arrangement is very different from anything on Earth. There are no floors and ceilings in the traditional sense. Every surface is a potential floor, every wall a potential ceiling. Astronauts orient themselves by the labeling and the positioning of equipment, and over time, they develop a natural, intuitive sense of which way is up in each module, even though up means nothing in microgravity. Some parts of the station have a conventional feel, with surfaces that the crew tends to treat as a floor and equipment mounted in a way that creates an up and down. Other sections are more disorienting, surfaces lined with equipment on all sides. The station is divided into roughly two main segments. On one side, the Russian segment, which has its own somewhat distinct feel, older in places and with systems that reflect Russian spacecraft design traditions. On the other side, the American segment, which also encompasses the European and Japanese laboratories. In between, connecting tunnels and nodes create a complex three-dimensional maze of rooms and passages that astronauts learn to navigate as naturally as you navigate the hallways of your own home. The station has been struck by tiny meteoroids and debris thousands of times. Space looks empty. In photographs taken from orbit, the background is pure black, scattered with distant and unreachable stars. But the environment around the station is in fact filled with debris, moving at extraordinary speeds. Pieces of old satellites, fragments from past rocket stages, flecks of paint, and naturally occurring micrometeoroids zip through low Earth orbit at speeds that turn even the tiniest particle into something more energetic than a bullet. Over the decades, the station's windows and outer hull have been pitted and marked by impacts too small to cause serious damage, but large enough to be visible. The windows of the Cupola module, the beautiful observation bay from which astronauts photograph the Earth, have shown small chips and marks from impacts over the years. These are reminders that space, as quiet as it looks, is not still. For larger debris, the station has systems to detect and track potential collision risks. Operators on the ground constantly monitor the trajectories of known debris objects and calculate whether any of them might come close enough to the station to be a concern. When a potential close approach is identified, mission controllers can plan and execute what is called a debris avoidance maneuver, firing the station's thrusters to gently nudge it into a slightly different orbit, stepping quietly out of the way of something traveling at 28,000 kilometers per hour. Most of the time, these maneuvers go unnoticed by the general public. They are just another part of the quiet, constant work of keeping people alive in space. The station has a carbon dioxide scrubbing system that removes the gas exhaled by the crew. In any enclosed space, breathing is a problem waiting to happen. Every breath you take pulls oxygen from the air and replaces it with carbon dioxide. On Earth, The vastness of the atmosphere takes care of this so efficiently that you never have to think about it. But inside the sealed hull of a space station, with only a few hundred cubic meters of air and a small crew exhaling steadily, carbon dioxide can build up to dangerous levels very quickly. The station uses several systems to manage this. The carbon dioxide removal assembly absorbs carbon dioxide from the cabin air and vents it overboard, out into space. The Sabatier system goes a step further, combining carbon dioxide with hydrogen to produce water, which can then be processed and used again by the crew. The oxygen generation system uses electricity to split water molecules into hydrogen and oxygen, replenishing the breathable air. The result of all these interlocking systems is that the air inside the station stays within very precise parameters. The right mixture of nitrogen and oxygen at the right pressure, with acceptable levels of carbon dioxide and humidity and trace contaminants. The crew breathes without thinking about it, the same way you do. But behind that effortless breath is an extraordinary web of technology, working every moment to make it possible. Astronauts aboard the station lose bone density and muscle mass without careful exercise. The human body evolved over millions of years under the constant pull of Earth's gravity. Every muscle you have, every bone, the shape of your heart and the flow of your blood, all of it developed in a world where gravity pressed down on you every moment of your life. Remove that gravity, and the body begins to adapt in ways that are deeply unhealthy for a return to Earth. In microgravity, bones no longer need to bear weight, so they begin to lose density. Muscles that were constantly working against gravity begin to weaken and atrophy. The spine, freed from compression, actually lengthens slightly, making astronauts measurably taller in space than they are on Earth, sometimes by as much as 5 centimeters. The cardiovascular system changes too, because the heart no longer needs to work as hard to pump blood upward against gravity. To counteract these effects, astronauts on the station exercise for approximately 2 hours every single day. The station is equipped with a treadmill, a stationary bicycle, and a device called the Advanced Resistive Exercise Device, which uses vacuum cylinders to simulate the resistance of weightlifting. Astronauts run and pedal and lift, strapped to their equipment with harnesses and bungee cords, so they do not simply float away from the machine. Even with all of this exercise, returning astronauts typically need weeks or months of rehabilitation on the ground to fully regain their pre-flight physical condition. Long-duration missions, lasting 6 months or a year, require even more careful management and longer recovery times. The human body is resilient, but it was not designed for this. The view of Earth from the station is unlike anything else in human experience. There is a module on the International Space Station called the Cupola. It is a small, dome-shaped observatory module added to the station in 2010, and it has 7 windows, 6 arranged around the sides and 1 pointing directly downward. It was designed primarily for observing and guiding robotic operations outside the station, but it has become something much more than that. It has become the most beloved room in one of the most extraordinary buildings ever made. From the Cupola, astronauts look down at the Earth from 400 kilometers above, and what they see defies easy description. The curvature of the planet is visible, that famous and quietly humbling arc that tells you, on a deep and wordless level, that you are somewhere else, that you have left the familiar behind. The atmosphere, from up there, looks impossibly thin. A thin blue haze hugging the surface, a membrane so fragile that it looks as though it could barely hold together. Astronauts describe the experience of looking down at Earth from the cupola in ways that sound like something between meditation and revelation. They see storms from above, vast spiral systems moving slowly across ocean surfaces. They see the wrinkled folds of mountain ranges, the silver threads of rivers, the brown expanse of deserts, meeting the green of forests at sharp, clean lines. At night, they see the lights of cities glittering below like grounded constellations, connected by the faint lines of highways. They see lightning flickering inside clouds, silent from up there, just pulses of blue and white light deep inside cotton towers. Many astronauts have described a shift in perspective that happens when they spend time looking down at Earth from the station. A feeling that national borders, invisible from space, are just human stories laid over an ancient and unified surface. A sense that the planet is small and precious and worth protecting. This feeling even has a name. It is called the overview effect, and it is one of the quieter, stranger gifts that the station has given to the people who have lived there. The station recycles nearly all of its water. Water is heavy, enormously, expensively heavy in the context of space travel. Launching a single kilogram of anything into low Earth orbit costs thousands of dollars, and water weighs a kilogram per liter. You cannot simply resupply a space station with fresh water the way you might resupply a remote Antarctic base. You have to be far more creative than that. The water recycling system aboard the International Space Station is one of the great marvels of applied engineering. It collects every possible source of moisture and processes it back into drinkable water. Humidity condensed from the air, the moisture in the crew's breath, sweat that evaporates from their skin during exercise and is then recaptured from the air. Even urine is processed. The water recovery system on the station uses a series of filtration and distillation processes to turn urine into water that is, by measured chemical composition, cleaner and purer than the tap water in most cities on Earth. Astronauts are told, and generally accept with good humor, that the water they drink today may have been something else entirely yesterday. The chemistry does not lie, the systems work, and the psychological distance between what something was and what it has become through filtration is something that the crews learn to let go of, because they have to, and because the water truly is clean. Today, the station recovers roughly 93% of all the water that enters the system. plans are in place to push that even further. For long-duration missions to the Moon and eventually Mars, systems like this will not be optional luxuries. They will be the only thing standing between a crew and disaster. The station's solar panels generate enough electricity to power approximately 40 average homes. 8 solar array wings extend from the station's truss structure like the wings of an enormous, angular butterfly. Each wing is made up of 2 panels, and together they cover an area of roughly 2,500 square meters. They are made of thousands of individual solar cells that convert sunlight directly into electricity, and when the station is in sunlight, they generate approximately 84 to 120 kilowatts of electrical power. That is enough to meet all of the station's needs and then some, powering the life support systems, the science experiments, the lighting, the computers, the communications equipment, the exercise machines, and the heating and cooling systems all at once. Excess energy is stored in batteries and used during the roughly 35 minutes out of every 90-minute orbit, when the station passes through the shadow of the Earth and the solar panels go dark. The solar panels have to be carefully oriented to track the Sun as the station moves through its orbit. There are mechanisms that rotate the wings slowly, keeping them pointed toward the light with a precise and patient attention that never wavers. Without that constant tracking, the panels would only be producing a fraction of what they need, and the station's systems would eventually fail. Over the years, the solar panels have aged and degraded slightly, as all things in the harsh environment of space do. Newer solar array upgrades have been installed during recent missions to maintain and improve the station's power generation capacity, ensuring that it can continue to support research and habitation well into the future. Astronauts on long-duration missions experience significant changes in fluid distribution in their bodies. One of the stranger and more immediate physical effects of arriving in space is something that every astronaut notices within the first hour or two of orbital flight. On Earth, gravity pulls fluid in your body downward. Your legs contain a significant amount of your total blood and body fluid simply because they are at the bottom, and gravity deposits fluid there over time. When you remove gravity, all of that fluid redistributes. It shifts upward toward the head and chest. The result looks and feels strange. Astronauts in space get what they describe as a full feeling in their head, a constant, mild congestion similar to hanging upside down, except that it never goes away. Their faces often look slightly puffy compared to how they look on Earth, because the fluid that would normally pool in the lower body has moved upward. Their legs, by contrast, can look thinner because the fluid that would normally be in them has migrated toward the core. This fluid shift also affects vision in a way that researchers have been studying carefully. The increase in fluid pressure inside the skull can push against the back of the eye, causing the eyeball to change shape slightly and resulting in changes to vision that persist even after returning to Earth. Many long-duration astronauts have needed updated prescriptions for glasses after their missions, and some have experienced more significant vision changes that take months to fully resolve. This is one of the areas of active research at the station, because understanding and eventually preventing these changes will be essential for any missions beyond low Earth orbit. The station has a gym that is used every single day. You might not picture a gym when you imagine a space station. You might picture control panels and instrument racks, windows looking out at the stars, sleeping bags strapped to the wall, and all of that is there too. But so is something that resembles, at least in function, if not in form, the kind of equipment you might find at a fitness center on Earth. The treadmill on the station is a motorized running surface fitted with a harness system that presses the astronaut downward against it so that running is actually possible in weightlessness. Astronauts can run for 30 minutes to an hour at a time, strapped in, going nowhere in the traditional sense, but maintaining the cardiovascular fitness and bone density that will allow them to walk normally when they return to Earth. The treadmill has a name, an acronym, a typically wonderful piece of NASA engineering creativity, where the name was apparently chosen to produce a particular set of letters that spells the last name of a well-known television personality who won a public naming contest. These things happen in space programs as everywhere else, and they are a reminder that the people who work in space science are human beings with senses of humor. The resistive exercise device mimics weightlifting. The cycle ergometer is a stationary bike. Together, these three pieces of equipment take up a modest amount of space by Earth standards, but represent an enormous investment in the long-term health of the crew. Exercise time is scheduled into every crew member's daily routine with the same priority as scientific experiments and maintenance tasks. It is not optional. The human body begins to lose condition in microgravity faster than most people realize, and 2 hours of daily exercise is what the research has determined is necessary to slow that process to a manageable rate. The Canadarm robotic system is one of the station's most essential tools. Canada's contribution to the International Space Station is, in its quiet way, one of the most remarkable pieces of technology on board. The space station remote manipulator system, which most people simply call the robotic arm, is a 15-meter-long mechanical arm that can move end over end along the outside of the station's truss structure like an inchworm crawling along a branch. It has 7 joints and can rotate almost 360 degrees at each one, giving it a range of motion that allows it to reach almost any point on the station's exterior. It has lifted spacecraft into position. It has caught uncrewed cargo vehicles arriving from Earth and berthed them against the station's docking ports. It has moved equipment and modules during construction. It has provided a platform for spacewalking astronauts to stand on and be maneuvered to precise locations on the station's exterior without having to climb there themselves. The arm is operated from inside the station by astronauts using a control station with cameras and displays, or from the ground by flight controllers at mission control. It moves slowly and deliberately, with an almost meditative patience, never rushing, always precise. Watching footage of it moving along the truss, reaching out to capture an arriving cargo vehicle, has a quality to it that is strangely calming. The careful, considered movement of something built for a purpose and doing exactly what it was made to do. There is also a smaller robotic arm called dextry, which attaches to the end of the main arm and can perform delicate manipulation tasks on the station's exterior, changing equipment and doing maintenance work that would otherwise require astronauts to suit up and go outside. Dextray has 2 arms of its own and various gripping tools, and it can work in the dark and in the cold, maintaining the station's exterior with a patience that never flags and a precision that human hands, even in the best gloves, would struggle to match. The station experiences 16 sunrises and 16 sunsets every single day. We touched on this briefly, but it is worth dwelling in for a moment, because there is something quietly extraordinary about it that deserves a little more space and a little more time. Every 90 minutes, the station completes 1 full orbit of the Earth. That means every 90 minutes, it moves from daylight into the shadow of the Earth and back into daylight again. From the crew's perspective, the sun rises and sets 16 times in every 24-hour period. The sun comes up, sometimes dramatically, a sudden burst of light after 35 minutes of complete darkness, and then climbs quickly across the sky and sets again just as fast. Astronauts describe the sunrises from orbit as among the most breathtaking things they have ever seen, because they are not looking at a sunrise from a point on the ground. They are moving toward it at 7.7 kilometers per second. The horizon goes from black to a thin line of blue to orange to gold in the space of a few seconds. Then the sun itself clears the edge of the Earth and everything floods with light. The station's solar panels pivot to face it. The batteries begin charging, and whatever darkness was present a moment ago is gone entirely. Despite this extraordinary lighting situation, the crew does not live by the rhythm of 16 sunrises a day. They live by a 24-hour clock set to Coordinated Universal Time, the same time zone used for international coordination on the ground. Lights in the station are dimmed in the evenings and brightened in the mornings to help maintain a day and night cycle that their bodies can understand. Alarms go off at a fixed wake time, regardless of whether the sun is in the window or not. The station's own rhythm is a human invention overlaid on top of the natural rhythm of orbit, a small act of insistence that the people inside are still, in some meaningful sense, creatures of the world below. Astronauts on the station can see the aurora from above. From the ground, the aurora borealis and aurora australis are among the most beautiful natural phenomena you can witness. Curtains and ribbons of green and pink, and sometimes red light rippling across the night sky, caused by charged particles from the sun interacting with gases in the upper atmosphere. People travel to the far north and far south of the world just to catch a glimpse. From the International Space Station, You see the aurora from above and from the side at the same time, and that view is different from anything you can see from the ground. From orbit, the aurora appears as an eerie, glowing ring or band encircling the magnetic poles. It shimmers and pulses in real time. Bands of green and red and violet light drifting and shifting across the upper atmosphere below the station. Astronauts have described floating to the cupola windows when word gets around that there is aurora visible, and simply watching. Not because they have to, not because it is scheduled, but because the view is simply too beautiful to miss. The station passes through or near the auroral oval on many of its orbits, and when solar activity is elevated, the light show can be spectacular. Photographs taken from the station of aurora have a surreal, otherworldly quality because they show the light from an angle that human beings never see from the ground, sweeping across the curve of the planet from above, with the deep black of space above and the gentle glow of cities below. From that altitude, an aurora does not just shimmer on the horizon. It is something you look down into, something that fills the space between you and the ground with shifting, living color. A curtain of light between the station and the surface of the Earth, soft and vast and ancient. The station grows plants as part of ongoing research into growing food in space. One of the questions that hangs over any vision of long-duration human spaceflight, the kind of missions that would take people to Mars or beyond, is food. You cannot carry enough food for a 3-year round trip to Mars. The weight and volume would be impractical. At some point, humans in space will need to grow some portion of their own food, the way humans on Earth have grown food for thousands of years. The station has a series of plant growth experiments that are working toward understanding how to make that possible. There is a small plant growth unit about the size of a carry-on suitcase, fitted with pink and purple LED grow lights that give it an eerie, slightly alien glow in the middle of an otherwise utilitarian laboratory. Astronauts have grown lettuce, kale, mustard greens, radishes, and various other leafy vegetables in these units, using specially designed plant pillows filled with a clay-based growth medium and fertilizer. When the first crops of lettuce were grown and harvested on the station, the crew had permission to eat some of them. The flavor, astronauts reported, was surprisingly good. Fresh, a little spicy, real. In a place where most food comes from sealed packages and pouches, a freshly harvested leaf of lettuce represents something that is difficult to overstate in its simple human importance. Beyond the smaller growth units, there are more advanced plant growth chambers on board that researchers use to study how plants behave in microgravity, how roots grow when there is no up or down, how flowering and seed development works in weightlessness, whether plants produce the same nutritional content in space as they do on Earth. These are quiet, patient experiments conducted in small chambers by people floating in orbit, building a foundation of knowledge that future generations of astronauts will depend on when they have to grow their own food far from Earth. The station's first module was called Zarya, which means sunrise in Russian. Names have meaning, and it is worth pausing on the fact that the very first piece of the International Space Station, the foundation of everything that would follow, was given the name Zarya, sunrise. The Zarya module was launched in November of 1998 aboard a Russian Proton rocket from the Baikonur Cosmodrome in Kazakhstan. It was a functional cargo module, not a habitation module, designed to provide the initial propulsion and power for the station's first years of operation until further components could be delivered and connected. It is roughly 13 meters long and 4 meters wide. It still orbits today, still connected, at the very end of the Russian segment of the station, more than 2 decades after its launch. 2 weeks after Zarya went up, the Space Shuttle Endeavour launched from Florida, carrying the second module, an American-built connecting node. The shuttle's crew used the robotic arm and then a series of spacewalks to connect the 2 modules in orbit. And in doing so, they created something that had never existed before: a connected, multinational structure in space. A handshake between 2 nations, in the dark, above the atmosphere. That word, Zarya, seems right for a beginning. The idea of the station as a kind of dawn, a first light of something new, a name chosen not for technical reasons, but for the way it sounds and what it means. Sunrise, the beginning of a day, the beginning of something that would take years to build and decades to inhabit, and perhaps centuries to truly understand. The station can be seen from the ground with the naked eye. On any given evening, if you know when to look, you can step outside and watch the International Space Station pass overhead. It appears as a bright, steady point of light, often brighter than any star, moving smoothly and quickly from horizon to horizon in about 5 minutes. It does not flicker, it does not blink. It simply moves, the way something purposeful and real moves when it is going somewhere. Websites and applications maintained by space agencies allow anyone with a location and an internet connection to find out exactly when the station will pass over their part of the world, what direction to look, and how high above the horizon it will appear. On nights when the geometry is right, it can pass almost directly overhead, a brilliant moving star that the whole neighborhood is technically watching at the same time, most of them without knowing it. There is something unusually moving about this experience, if you let yourself feel it. You are standing in your backyard, or on a balcony, or in a park, and you are watching a point of light cross the sky. And inside that point of light, right now, there are people, living human beings, floating in a laboratory, possibly sleeping, possibly eating dinner, possibly pressing their faces against a window and looking down at the dark side of the earth, watching city lights scroll past below them and wondering which one might be yours. The station has hosted more than 270 people from over 20 different countries. Every person who has ever lived aboard the International Space Station arrived there as a stranger to the experience and left as someone changed by it. Changed in ways that are sometimes dramatic and visible, like the physical effects of microgravity on the body, and sometimes quieter and more lasting, like the shift in perspective that comes from spending months looking down at the whole of the human world from above. The roster of station visitors includes people of remarkable diversity, men and women, young crew members and older ones, scientists and military pilots, people who grew up in small towns and people who grew up in major cities, people who had dreamed of spaceflight since early childhood and people who came to it later in life through other paths, teachers, physicians, biologists, physicists, engineers, and commanders. They have come from the United States, Russia, Japan, Canada, Italy, France, Germany, the Netherlands, Belgium, the United Kingdom, Sweden, Denmark, Norway, Spain, Brazil, South Korea, South Africa, Malaysia, Kazakhstan, and other nations. Each of them brought their own language and their own culture and their own family back on the ground and their own way of seeing things, and each of them was changed by the same experience, by the same view, by the same particular quality of light coming through the cupola windows during a sunrise over the Pacific. The station has a smell that every astronaut notices. This is one of those facts about the station that you do not find in the technical manuals. You find it in the memoirs and interviews of the people who have been there. The International Space Station has a smell. Astronauts returning from a spacewalk who have been outside in the vacuum of space in their suits describe noticing it when they remove their helmets back inside the airlock. A sharp, slightly metallic, electric smell that some compare to welding or burning metal, others to seared steak, others to something more like gunpowder. It clings to their suits and gloves. It fades after a few minutes inside the station as the scrubbed and regulated station air dilutes it, but it is unmistakably there every time. Space itself, of course, is a vacuum and has no smell in the traditional sense. What the astronauts are picking up is thought to be the result of atomic oxygen in the very upper reaches of the atmosphere interacting with the materials of their suits, or possibly volatile compounds released from reactive particles in the environment, clinging to the exterior surfaces of their equipment. Inside the station itself, away from the airlock, the air has its own character. Astronauts describe it as clean but slightly stale, with undertones of machinery and electronics. There are sometimes stronger smells when food is being prepared, which the crews tend to find deeply comforting, a reminder of kitchens and home. The warm, slightly sweet smell of reconstituted scrambled eggs in the morning, coffee, heating, something baking, if the right kind of food packet is involved. The smell of something ordinary in an extraordinary place. The station has hosted hundreds of scientific experiments across dozens of disciplines. One of the things that makes the International Space Station more than an engineering achievement or a symbolic gesture of international cooperation is what actually happens there day to day. The station is, at its heart, a laboratory, a research facility floating in conditions that cannot be replicated anywhere on Earth. Hundreds of experiments have been conducted aboard the station since it became operational. They span an enormous range of disciplines: biology and biotechnology, studying how cells and organisms behave in microgravity, how bacteria evolve when they are no longer under gravity's influence, how the human body changes over months in orbit, Earth and space science, using the station's unique vantage point to observe the planet below, the atmosphere, the oceans, and the space environment around it. Physics and materials science, taking advantage of the near-perfect microgravity environment to study phenomena that are impossible to observe on Earth, where even the most sensitive experiments are disturbed by the constant vibration and weight of the world. Medical research conducted on the station has already yielded insights that have benefited patients on Earth. Studies on bone density loss in astronauts have contributed to better understanding of osteoporosis. Research on muscle atrophy has informed treatments for patients who are bedridden for long periods. Experiments on protein crystal growth, conducted in the perfect stillness of microgravity, have produced crystals of extraordinary clarity that have allowed researchers to study the molecular structure of proteins involved in diseases including cancer. The station is, in the truest sense, a laboratory in the sky. Its output is not just adventure and inspiration. It is data, measurements, peer-reviewed papers, small and quiet contributions to human knowledge that accumulate over years and decades into something meaningful. Sleeping in space is done in small private compartments that astronauts often personalize. For something that sounds as simple as rest, sleeping on the International Space Station requires some careful thought and a bit of getting used to. In microgravity, there is no comfortable surface to lie down on. There is no mattress, no pillow, no bed frame. You float. And floating while you sleep, while actually quite comfortable once you adjust to it, comes with its own complications. The most notable is that you might drift. If you fall asleep in the middle of a module and do nothing to secure yourself, you will float gently around the module as you sleep, bumping into walls and equipment, potentially drifting into sensitive areas. So astronauts sleep in sleeping bags, but not bags that lie on a surface. Instead, the bags are mounted to the walls of small personal sleeping quarters, roughly the size of a phone booth, one per crew member. The crew quarters on the American side of the station are small but private. Astronauts can close a sliding panel or curtain across the entrance to create a space that is, within the constraints of the situation, their own. They personalize them with photographs from home, with small items they brought from Earth. A child's drawing, a card from a partner, a good luck charm given by someone they love. The sleeping bags are designed so that the astronaut slides in and zips up, with their arms either inside or, as many prefer, floating free outside at their sides. Because there is no gravity to make a pillow useful, some astronauts wear soft headbands to keep their head from drifting and bumping gently against the walls of the bag as they sleep. The temperature and air circulation in the crew quarters can be adjusted individually, giving each person a small measure of control over their sleeping environment. Reports from astronauts about the quality of sleep in space vary. Some find it extraordinarily restful, especially after the initial adjustment period. The absence of the vibration and noise of Earth life, the perfect stillness of floating in a sleeping bag in the quiet hum of the station, can produce sleep that is deep and dreamless. Others struggle, particularly early in a mission, as their bodies adjust to the changed fluid distribution and the absence of gravity. Almost all of them report vivid and unusual dreams. There is something touching about imagining this. The astronaut floating in their sleeping bag in their small private room, the photographs from home pinned carefully to the wall, the hum of the life support systems, a steady and reassuring background, the Earth rotating slowly below them outside the hull. The same rituals as any night, anywhere. Eyes closing, breath slowing, the world going quiet. The station has been used to study how fire behaves in microgravity. Fire on a space station is one of the most serious emergencies imaginable. In a sealed, pressurized environment with nowhere to go and no firefighting aircraft to call, a fire is an immediate threat to life. The station has fire detection and suppression systems, and the crew trains extensively for fire emergencies. But beyond the safety systems, fire itself is also a subject of scientific interest in space. On Earth, fire burns with a familiar teardrop shape. The hot gases produced by combustion rise through convection, drawing in fresh oxygen from below and creating that distinctive upward-pointing flame. In microgravity, there is no convection. Hot gases do not rise because there is no up. A flame in microgravity forms a sphere, a round ball of blue and sometimes faintly yellowish fire, spreading outward in all directions equally. Experiments conducted in the station's combustion research rack have studied how various materials burn in these conditions. The research has practical applications for designing fire suppression systems for future spacecraft. It has also revealed some genuinely unexpected phenomena. Researchers found that flames they believed had gone out were in some cases continuing to burn in a cold, dim, nearly invisible mode called cool flames. These cool flames burn at temperatures and through chemical reactions that are different from normal combustion, and they produce different byproducts. This was not something researchers had predicted. It was a discovery made possible by the unique environment of space, where the absence of gravity removed variables that had always been present in combustion research on Earth and revealed something that had been hidden underneath. The station has a way of doing that, of stripping away the assumptions we carry from growing up on the ground and showing us what is underneath them. The station receives regular cargo deliveries from multiple countries. Life on the station depends on a supply chain that begins on the surface of the Earth and ends weeks or months later at a docking port 400 kilometers up. Everything the crew needs that is not produced on the station itself must be sent up: food, water, spare parts, equipment for experiments, clothing, personal items requested by the crew, medications, tools. The supply chain for the International Space Station is one of the most carefully managed logistics operations on the planet. Cargo vehicles come from multiple directions. American commercial providers send cargo missions on a regular schedule, their uncrewed spacecraft either docking autonomously with the station or being captured by the robotic arm and berthed to a port. Russia's Progress cargo spacecraft have been delivering supplies to the Russian segment since before the station was even assembled, having served an earlier Russian space station before being adapted for the International Space Station. Japan contributed a cargo vehicle called Koinotori, which means white stork, which delivered large amounts of cargo and was particularly useful for bringing oversized items. The European Space Agency operated its own cargo vehicle, which made 5 flights to the station and delivered enormous quantities of supplies, including propellant used to maintain the station's orbit. The contents of a cargo mission to the station are fascinating to think about. Alongside the scientific equipment and spare parts and water bags, there will be a small selection of personal items chosen by the crew. Fresh fruit, if it can survive the journey, is an extreme luxury on the station. Astronauts have described receiving an orange or an apple as one of the great joys of a long mission. The smell of fresh fruit in the station's recycled and mechanical smelling air, the taste of something that grew in soil under actual sunlight, ordinary miracles in extraordinary places. The station orbits in a region that was only accessible to humans beginning in the 20th century. The altitude of 400 kilometers is, in geological and cosmological terms, essentially nothing. It is a hair's breadth above the surface of the Earth. And yet, for the entirety of human history, until less than a century ago, it was as unreachable as the surface of another planet. The technologies required to put something there and keep it there, powerful chemical rockets, precision orbital mechanics, advanced materials science, computerized guidance systems, did not exist until within the lifetime of some people who are still alive today. The first human being to reach orbit was Yuri Gagarin, a Soviet cosmonaut, in April of 1961. He circled the Earth, once in a capsule, not much larger than a phone booth, and returned. The entire flight lasted 108 minutes. The technology that accomplished it was astonishing for its time, but primitive compared to what would follow. Less than 40 years separated Gagarin's first orbital flight from the launch of the first module of the station. In that time, human spaceflight went from a single man in a small capsule on a single orbit to a permanent habitation facility the size of a football field, built by multiple nations, hosting ongoing scientific research and continuous human presence. The speed of that development, measured against the pace of previous technological change, is extraordinary, and the station itself has now been inhabited for more than 2 decades. It has outlived its original planned service life. It has been repaired, upgraded, supplemented, and extended. Its operational life has been extended multiple times as the nations operating it have decided that what it offers is worth maintaining. It is, in some ways, the oldest thing in space that humans have built with the intention of living in. A structure that has accumulated the kind of history that only comes with time and continuous use. The station was almost cancelled multiple times during its development. The story of the International Space Station is not only a story of cooperation and achievement. It is also a story of close calls, budget fights, political arguments, and moments when the whole project nearly came apart. The origins of the station lie in an American plan called Space Station Freedom, which was proposed in the 1980s and went through so many redesigns and budget reductions over the following years that it became something of a running joke in the space community. By the early 1990s, the project was in serious trouble. It had spent billions of dollars and had little to show for it physically. The design had changed so many times that some wag renamed it Space Station Almost. Congress repeatedly threatened to cancel it entirely. The solution came from an unexpected direction. The end of the Cold War opened the possibility of involving Russia in the project. Russia had deep and real expertise in long-duration spaceflight from its Mir station program, and including them would both reduce costs and create a partnership that had political value beyond the purely technical. The deal that brought Russia into the project transformed Space Station Freedom into the International Space Station and gave the project the momentum it needed to survive. Even after construction began, the project faced near cancellation. A vote in the United States House of Representatives to cancel the station failed by a single vote. One vote. The margin between the International Space Station existing and not existing was, at one critical moment, a single member of Congress. Funding shortfalls delayed construction schedules. A space shuttle disaster in the early 2000s grounded the shuttle fleet for more than 2 years and severely disrupted the assembly schedule. There were years when the station was maintained by crew sizes reduced to 2, when scientific research was largely suspended and all effort was directed towards simply keeping the structure functional. That it survived all of this and became what it is today is partly a testament to the technical excellence of the people involved, and partly a testament to something harder to quantify, a belief, maintained through budget fights and disasters and political arguments, that this thing was worth building and worth keeping. A quiet and persistent conviction spread across multiple countries and multiple generations of engineers and scientists and politicians that human beings should have a home in space. The station travels over the ocean for much of every orbit. The Earth is mostly water. Just over 70% of its surface is ocean, and this means that most of the station's orbital track, as the planet rotates beneath it, passes over sea rather than land. For hours at a time, looking down from the cupola, you might see nothing but ocean stretching in every direction to the curve of the horizon. From 400 kilometers up, the ocean is not the grey and heaving thing it can seem from a ship on its surface. It is blue, extraordinarily, vividly, variably blue. The shallow tropical waters near islands and coasts glow turquoise, so clear that the coral structures beneath them are sometimes visible from space. The deep, open ocean is a darker blue, almost violet in the parts where depth is greatest. Ocean currents show themselves as subtle shifts in color, temperature differences expressing themselves in the spectrum of light that the water reflects. Clouds cast moving shadows on the surface. Storms look, from above, like vast and slowly rotating cotton formations, their internal structure revealed by the way light plays across their peaks and valleys. From up there, a hurricane is a beautiful thing, its spiral arms reaching outward from a clear and eerily calm center, the eye. Beautiful and terrible, the way some of the most powerful natural phenomena are, when you see them from enough distance to take in their whole shape. The station can see these things and record them. Its cameras and sensors are among the most continuously active Earth observation tools in existence, providing data on ocean temperature, cloud patterns, atmospheric composition, and sea surface height that complement satellite observations and ground-based measurements. Every orbit over the ocean is also an orbit of scientific observation. The station has a library and entertainment system for the crew's personal time. It is a digital one, stored on the station's computer systems, not shelves of physical books, though some astronauts do bring physical books and personal reading material with them. But the digital library aboard the station includes an enormous collection of reading material, films, music, and other entertainment that crew members can access during their personal time. Personal time is scheduled into the crew's day, just as exercise and sleep are. A few hours each weekend, in particular, are designated free time, and what astronauts choose to do with that time says interesting things about human nature. Some read, some watch films, some play music. Several astronauts over the years have been accomplished musicians, and instruments have been brought to the station, including guitars and a saxophone. One Canadian astronaut became particularly well known for recording music from the station and sharing it with Earth, including a performance of a famous David Bowie song that was watched by millions of people and remains one of the most quietly remarkable moments in the history of human spaceflight. The idea of someone floating in orbit, strumming a guitar in weightlessness, the strings vibrating in the hum of the station's systems, the music traveling down to the ground and out across the internet to millions of people in their houses and offices and on their phones, all of them for a moment connected to something 400 kilometers above them by the simple and ancient technology of a song, is one of the things that makes the station feel, at its best, like a genuinely human place. The station also has communication links that allow the crew to make video calls to their families on Earth. The connection has some latency, a brief delay caused by the signal traveling up and back, but not enough to make conversation feel impossibly fragmented. Astronauts on long missions can call home, can see the faces of their children, can be there in some sense for birthdays and holidays and ordinary Tuesday evenings when nothing special is happening. These connections matter enormously for crew morale and for the families on the ground who have to carry on with daily life while someone they love lives in orbit. The station has experienced more than 230 spacewalks. A spacewalk, or more precisely, an extravehicular activity, is an event in which an astronaut leaves the pressurized interior of the station and moves out into the vacuum of space, tethered to the exterior of the station by safety cables, wearing a spacesuit that contains everything they need to survive. It is one of the most physically demanding and mentally focused activities that an astronaut performs, and in its way, one of the most extraordinary things a human being can do. Preparation for a spacewalk begins well in advance. The crew must spend hours breathing pure oxygen before going out, to purge their blood of dissolved nitrogen that could otherwise form dangerous bubbles if they move too rapidly from the station's atmospheric pressure to the lower pressure inside the spacesuit. The suits themselves must be meticulously checked and configured. The tools and equipment to be used outside must be prepared and tethered carefully, because dropping a tool in orbit means it becomes its own satellite, drifting away and eventually lost. A detailed plan is rehearsed and reviewed until everyone on the crew and the ground teams knows exactly what will happen and what will happen if something goes wrong. Then the airlock is depressurized, the outer hatch opens, and the astronaut floats out into space. The view from outside the station during a spacewalk is described by every astronaut who has done one as one of the most intense experiences of their lives. The Earth is below, enormous and impossibly bright and slowly moving. The station extends around you, its solar panels and modules and trusses going off in multiple directions. A structure that from this vantage point finally looks its true size. And beyond everything, in every direction not occupied by the station or the planet, there is the absolute black and silence of space, scattered with unblinking stars. Spacewalks during the assembly of the station were sometimes 8 hours long or more. Astronauts worked by hand in those conditions, fitting structural components, connecting electrical cables, assembling joints and bolts with pressurized gloves that make delicate work much harder. They did this in darkness and in blazing sunlight, in temperatures that swung by hundreds of degrees, in a place where a single mistake could be fatal. They did it anyway, carefully and methodically, bolt by bolt and cable by cable, building something that would outlast them. More than 230 of these activities have been carried out at the station. Thousands of hours of human presence in the vacuum of space, building and maintaining and repairing. Each one is a small story of preparation and care and quiet courage. Fire behaves differently aboard the station than anywhere on Earth. On Earth, Fire has a familiar shape. A candle flame stretches upward into a teardrop point because the hot gases it produces are lighter than the cooler air around them, and gravity pulls the cooler air downward and inward, feeding fresh oxygen to the base of the flame and pushing the hot gases up into that characteristic elongated form. The shape of every campfire, every gas burner, every struck match you have ever seen is the shape that gravity gives to burning. On the station, in microgravity, there is no gravitational convection. Hot gases do not rise because there is no up for them to rise toward. Instead, a flame in microgravity burns as a small, nearly perfect sphere, glowing faintly with a cooler, bluer light than its Earth counterpart. It consumes the oxygen immediately around it and produces carbon dioxide and water vapor in a tiny shell around itself, and without the convective flow that on Earth would carry fresh air to it, it tends to burn at lower temperatures and with less intensity. This changes almost everything about fire safety aboard the station. The crew trains extensively for fire scenarios, and the station carries fire suppression equipment. But the behavior of fire in microgravity is different enough from fire on Earth that the training is specialized. A smoldering fire in microgravity can be difficult to detect at first because it produces less visible flame. Smoke particles, without gravity to cause them to rise, can disperse in unexpected directions. The station's air scrubbing systems help detect combustion products early, and the crew carries out regular drills to ensure they know how to respond. Fire is one of the scenarios aboard the station that is taken most seriously. In a sealed environment with no immediate possibility of evacuation, a fire is not an emergency you can simply escape from. The response must be fast, disciplined, and effective, and the engineers and trainers who prepared for this scenario had to think carefully about how to prepare crews for a threat that behaves by different rules than anything they had encountered before. The station is slowly losing altitude and requires regular boosts to maintain its orbit. The station orbits in what is technically referred to as low Earth orbit, but even at 400 kilometers, the atmosphere is not completely gone. The extreme upper reaches of the atmosphere exist even at that altitude, a region so thin that it is essentially a vacuum, but not quite a perfect one. The molecules up there are so sparse that the distance between them is enormous, but they are present. And as the station moves through them at 7.7 kilometers per second, they create a tiny but real drag force. Over weeks and months, this atmospheric drag gradually lowers the station's orbit. If nothing were done about it, the station would eventually decay into the denser lower atmosphere and burn up, just as uncontrolled spacecraft eventually do. To prevent this, the station's orbit must be regularly boosted back up. Thruster firings, either from the station's own thrusters or from visiting spacecraft that are docked and can fire their engines to push the station higher, are performed periodically to maintain the desired altitude. These boosts are part of the quiet, constant maintenance of the station. They happen without fanfare. Sometimes during the night, during the crew's sleep time, invisible to anyone not watching the orbital mechanics data. A brief firing of thrusters, a slight nudge upward, and then the station continues on its way at the altitude it has always been. The atmospheric drag that tried to pull it down temporarily reversed. The eventual end of the station will come in a controlled descent. When the nations operating it decide that it has reached the end of its useful life, a series of deliberate firings will lower its orbit gradually until it enters the upper atmosphere and the friction begins. The structure is too large and too massive to burn up completely. Parts of it will survive re-entry. The plan is to target it over a remote stretch of the South Pacific Ocean called Point Nemo, the most remote place on Earth's surface from any land, more than 2,000 kilometers from the nearest coastline in any direction. Point Nemo is already a graveyard for spacecraft. Hundreds of controlled descents of old satellites and space stations have been targeted there over the decades. When the International Space Station finally comes down, it will join them there, at the bottom of the deepest, most remote ocean on the planet, the final resting place of the largest structure humanity has ever placed in space. The station uses water recycled from every possible source aboard. Water is heavy. Carrying water from Earth to space costs an extraordinary amount in fuel and effort, which means that every drop of water on the station is precious, in a way that water almost nowhere on Earth is precious. And the solution that engineers arrived at for managing water on the station is one of those things that sounds strange at first, and then, when you think about it carefully, reveals itself to be quietly elegant. The station recycles water from almost every source available. Astronaut urine is processed through the water recovery system, filtered and purified through a multi-stage process that removes contaminants and adjusts the chemical balance until the result is water that meets stringent purity standards. Humidity is collected from the cabin air, including the moisture from astronauts breathing and sweating, and that too is filtered and returned to the supply. Water used for washing is processed and returned to the cycle. The result is a closed-loop system in which roughly 90% of all water aboard the station is recovered and reused. The water an astronaut drinks today may have been, in a previous form, sweat or breath or something more personal entirely. Astronauts are generally aware of this and tend to accept it philosophically. One astronaut famously said that the coffee made from recycled water tasted just as good as coffee on Earth, which is either a testament to the quality of the recycling system or to the remarkable power of needing a hot drink in the morning. The station also receives fresh water deliveries from visiting cargo spacecraft, which is used to top up the supply as losses occur. But the recycling system reduces the frequency and volume of those deliveries significantly, stretching the station's resources in a way that will be even more critical when future spacecraft travel too far from Earth for regular resupply missions to be possible. Water, that most ordinary substance, the thing that covers most of the surface of our planet and fills our cups and falls from the sky, takes on a completely different meaning in a place where every molecule must be accounted for and reclaimed and reused. On the station, nothing is wasted. Everything that can be kept is kept. The station has a dedicated observation module called the Cupola with 7 windows. If you asked an astronaut which part of the station they love most, the answer would not always be the same. Some love the quiet of their personal sleeping quarters. Some love the Japanese laboratory with its dedicated experiment racks. Some love the nodes where corridors intersect and the geometry of the station becomes tangible, where you can look along 3 or 4 tunnels simultaneously and feel the scale of the place. But many, perhaps most, would say the Cupola. The Cupola is a small observation module attached to the Earth-facing side of the station. It protrudes slightly from the main structure, and its 7 windows, 6 trapezoidal windows arranged in a ring around a single large circular window in the center, give a panoramic view of the Earth below and the space surrounding the station. The central circular window is the largest window ever flown in space, approximately 80 centimeters across, and through it, the Earth fills the view in a way that no photograph can quite replicate. Astronauts use the Cupola for official purposes, including operating the station's robotic arm during cargo operations and performing Earth observation research. But they also use it the way anyone would use a window with an extraordinary view. They go there in their free time. They float in the Cupola in the dark and watch the Earth move below them. They photograph the continents and the storms and the slow sweep of day turning to night across the surface of their home world. The light that comes through the Cupola windows changes constantly as the station moves through its orbit. During the sunlit portion of the orbit, the light is brilliant and direct, almost painfully bright when it catches the white solar panels or the reflective surfaces of other modules. As the station enters the Earth's shadow, the light changes slowly through blue and violet, and then into a darkness lit only by the stars and the glow of cities below. And then the sun appears again at the far limb of the Earth, an arc of fire and color that expands rapidly into full sunrise as the station moves through its arc. In the Cupola, these sunrises happen 16 times a day. 16 sweeping, unhurried passages of light and color through those 7 windows. Some astronauts have said that it is impossible to sit in the Cupola during a sunrise and not feel, viscerally and completely, that existence is a gift, that the universe is a generous place, that whatever difficulties and complications and worries they carried up from Earth are, from this height and with this view, manageable and temporary and small. The station's robotic arm system is one of the most sophisticated ever built. When the first modules of the station were being assembled in orbit, engineers faced a problem that had no precedent. How do you move large, heavy components in the weightless environment of space? You cannot use cranes the way construction workers use them on Earth, because there is no up or down, no ground for the crane to stand on, no gravity to assist in carefully lowering a heavy object into position, and you cannot do it entirely by hand, because some of the components to be assembled are far too large and too massive for astronauts in spacesuits to handle safely. The solution was the Canadarm2, a robotic arm system built and contributed by the Canadian Space Agency. Canadarm2 is roughly 17 meters long when fully extended, with 7 motorized joints that allow it to bend and reach in almost any direction. Unlike a conventional robotic arm that is fixed at one end, Canadarm2 can walk along the exterior of the station by anchoring itself alternately at either end, using a series of anchor points distributed across the station's outer surface. In this way, it can reach virtually any part of the station's exterior, repositioning itself methodically like an enormous mechanical inchworm. The arm has been used to capture visiting spacecraft, gently grabbing them as they approach and berthing them to the station's docking ports. It has been used to move astronauts on spacewalks, carrying them to work sites on distant parts of the station that would otherwise require a long and potentially risky translation along the outside of the structure. It has been used to move and position new modules during the assembly phase, placing components weighing tens of thousands of kilograms with a precision measured in centimeters. There is something almost living about the way Canadarm2 moves. It is slow and deliberate, the joints articulating smoothly, the arm extending and bending and repositioning with a kind of careful patience. Watching it operate from inside the station, or in footage captured by external cameras, it looks less like a machine and more like something organic, feeling its way along the surface of the station in the dark. Canada's contribution to the station through this arm is woven into almost every major operation the station has ever performed. The arm is not a peripheral feature. It is a central part of the station's ability to function. Small country, vast contribution, anchored permanently to the outside of humanity's home in space. The station passes over almost every inhabited place on Earth. The orbit of the International Space Station is inclined at approximately 51.5 degrees to the equator. This means that the station's ground track, the line on the Earth's surface directly below it as it orbits, sweeps north and south between roughly 51.5 degrees north latitude and 51.5 degrees south latitude. Within that band lies the vast majority of the human population of Earth. In practical terms, this means that the station passes over North America, Europe, Russia, China, Japan, Australia, South America, Africa, and the Middle East on a regular basis. It passes over the farms and the forests and the cities and the coasts. It passes over every major metropolitan area on Earth that lies within its orbital inclination. It passes over the place where you are right now. In all likelihood, this means that any person in those latitudes, on any clear evening when the geometry is right, can step outside and watch it go by. No telescope needed, no special equipment, just the knowledge of when to look and where. A bright, steady, moving point of light carrying human beings through the sky above your head. Some people make a practice of this. They follow the station's schedule and they go outside on the right evenings and they watch. Sometimes they wave, though they know perfectly well the crew cannot see them from that altitude. But they wave anyway, the same way you might wave at a ship passing in the harbor even when you have no connection to anyone aboard, because it seems like the right thing to do, because the acknowledgement feels true. The station has been visited by spacecraft from multiple countries and commercial providers. In the early years of the station's operation, the vehicles that served it were operated exclusively by government space agencies. NASA's Space Shuttle was the primary crew and cargo vehicle for the American side of the program, capable of carrying large payloads and multiple crew members and performing complex assembly operations. Russia's Soyuz spacecraft carried crew to and from the station on the Russian side, as it had been doing since the earliest days of human spaceflight. After the Space Shuttle program ended in 2011, the Soyuz became the sole means of getting crew to and from the station for several years, a period that was simultaneously a constraint and a quiet demonstration of how essential the Russian-American partnership had become. During those years, every American astronaut who went to the station rode in a Russian spacecraft from the same Baikonur Cosmodrome in Kazakhstan, where cosmonauts had been launching since the very beginning of the space age. Then, in the years that followed, commercial spaceflight arrived at the station's doorstep. Companies that had not existed when the station was first assembled began developing and flying their own spacecraft. The American company SpaceX began delivering cargo to the station with its Dragon capsule, and eventually developed a crewed version of the Dragon that began carrying astronauts. Another American company, Northrop Grumman, began flying Cygnus cargo spacecraft. Axiom Space has arranged private missions. The station, originally a structure built entirely by government programs, began receiving visitors from the commercial sector. This shift is significant in ways that extend beyond the station itself. The fact that private companies can now reach the station, can dock with it and deliver supplies and eventually crew, represents a broadening of access to low Earth orbit that was not possible in the station's early years. The station became, in this way, not just a research platform and a symbol of international cooperation, but also an anchor point for a growing ecosystem of commercial space activities. Other cargo vehicles from Japan and Europe also served the station over the years. Japan's H-2 transfer vehicle, called Kunotori, which means white stork, flew multiple missions carrying supplies and experiments. Europe's automated transfer vehicle carried fuel and cargo on several missions. These vehicles were not small achievements. They required their own years of development and testing and represented significant national investments in the capability to operate in space. The station is a node in a growing web of human presence in space, a place that multiple nations and now multiple companies can reach, and that connection grows richer as the years pass. The station's position relative to the Sun changes as it orbits, creating dramatic lighting conditions. Photography from the International Space Station is some of the most extraordinary photography ever taken by human beings, and a significant part of what makes those images so remarkable is the light. The light in low Earth orbit does not behave the way light behaves anywhere on the surface of the Earth. There is no atmosphere to diffuse it. Sunlight in space is raw and direct and blindingly intense, casting shadows of absolute darkness with knife-sharp edges. A solar panel in direct sunlight is almost painful to look at. The shadow behind a module is a pure, deep black, with no softening of the edges, no scattering of light into the shade. The contrast between illuminated surfaces and shadowed ones is total and extreme, and because the station moves so quickly through its orbit, this quality of light changes constantly. In the span of one orbit, a 90-minute loop around the planet, the light goes from the deep black of full shadow, when the Earth blocks all direct sunlight, to the blazing white of full solar exposure, and through every gradation in between. During twilight, when the station is at the boundary between day and night on its orbit, the light turns the most extraordinary colors. Shades of orange and gold and deep red, the sunlight passing through the thicker layers of the upper atmosphere at a shallow angle, refracted and scattered into colors that last for only minutes. Astronauts, who are accomplished photographers, and many of them become very accomplished during their missions, learn to anticipate these lighting conditions. They know which orbits will produce certain kinds of light over certain parts of the world. They position themselves at the cupola windows at the right moments to catch particular effects. The sunrise over the Himalayas, the city lights of Europe emerging as the station crosses from day to night over the Atlantic, the way the Sahara looks in the raking, low-angle light of an orbital afternoon. The photographs that result are not merely documentation, they are art. They show the Earth in ways that no photographer on the ground can replicate, from an angle and under lighting conditions available only to people in orbit. They show weather systems as sculpture, great spiraling forms of cloud and storm. They show the thin blue line of the atmosphere against the black of space, a line so thin relative to the size of the planet that it is almost shocking. They show the planet at night as a glowing, jeweled thing, its cities marking the coastlines and river valleys where human civilization has settled over thousands of years. These images come home with the astronauts and flow out into the world through social media and space agency archives, and they do something that is difficult to fully explain. They change how the people who see them think about the planet, about the atmosphere, about the cities of light scattered across the dark side of a blue world spinning in the cold. The station serves as a relay point for communications, research, and technology testing. The station sits in an extraordinarily useful position for testing new communications technologies. It is in space, which means it can test how signals behave in the space environment. It is in low Earth orbit, which means it is close enough for ground-based systems to communicate with it reliably while also being distant enough to present real communications engineering challenges. And it is continuously occupied, which means experiments can be monitored and adjusted in real time. Laser communications experiments have been conducted from the station, testing the use of focused laser beams to transmit data between the station and the ground at rates far higher than traditional radio communications allow. Quantum communications research has been conducted there, exploring the possibility of transmitting information using the principles of quantum mechanics in ways that would be fundamentally secure against eavesdropping. Technology for satellite constellation management and inter-satellite communications has been tested from the station's vantage point. Some of these experiments have very direct applications to the future of how human beings communicate. Laser communications, if it matures, could transform how spacecraft relay data to Earth, how scientific observations from deep space are transmitted back, and eventually how a network of communications satellites in orbit covers the globe with high-speed data access. The station is, in this sense, a test bed, not just for how humans live in space, but for how the infrastructure of space will develop in the decades ahead. None of this is glamorous in the way that spacewalks are glamorous or the way the Cupola view is beautiful. It is technical and incremental and patient. But that is the nature of a great deal of what happens on the station. The daily accumulation of careful work, the patient testing of ideas that may take decades to reach their full expression, the building of knowledge and capability that is invisible right now but will matter enormously later. The station experiences both extreme cold and extreme heat within minutes of each other. The thermal environment of the International Space Station is one of the most challenging aspects of operating there, and the engineering solutions that keep the crew comfortable inside represent some of the most sophisticated temperature management systems ever built. When the station is in full sunlight, solar radiation heats exposed surfaces to temperatures that can exceed 120 degrees Celsius. When it passes into the shadow of the Earth, those same surfaces begin to cool rapidly, and in the full shadow, temperatures on uninsulated surfaces can drop to nearly minus 150 degrees Celsius. This swing of more than 250 degrees happens multiple times in every orbit, over and over, day after day, year after year. The materials used in the station's construction must survive this repeated thermal cycling without cracking or degrading. The station is covered in multi-layer insulating blankets, layer upon layer of thin, reflective materials, separated by vacuum gaps that prevent heat transfer. The outer surfaces are coated with special materials that balance the absorption of solar radiation with the emission of heat, keeping temperatures within manageable ranges. Inside, the thermal control system uses a network of pipes carrying ammonia as a coolant. Waste heat from the electronics, the life support systems, the crew's bodies, and everything else that generates heat inside the station is collected by this coolant loop, circulated to large external radiators, and radiated away into space. The radiators are thin rectangular panels attached to the station's truss structure, and they glow faintly in the infrared as they shed the station's waste heat into the void. The crew inside experiences none of this directly. The temperature in the habitation modules is kept comfortable, roughly 22 degrees Celsius year-round. The drama of the external thermal environment is entirely invisible from where the astronauts live and work. They move through a space that feels like a well-managed office building, while all around them, just centimeters outside the hull, the temperature swings wildly enough to destroy unprotected metal. That is, in its own quiet way, one of the most remarkable things about the station. The contrast between what the crew experiences inside and what the laws of physics demand outside, bridged by systems so well designed that the transition is invisible, engineering that makes the impossible feel ordinary. The station has been home to several record-breaking missions. Long-duration spaceflight is its own discipline, separate from the engineering and science of the station itself. It is the study of what happens to a human being who stays in space not for days or weeks, but for months, and eventually approaching a year. The station has been the setting for some of the most significant long-duration missions ever flown. Scott Kelly of NASA and Mikhail Kornienko of Roscosmos spent approximately a year aboard the station together on a mission specifically designed to study the effects of very long-duration spaceflight on the human body. Scott Kelly's twin brother, Mark Kelly, who is also an astronaut but stayed on Earth, served as a control subject for the research, allowing scientists to compare the biological changes in Scott directly against those of a genetically identical person who remained in normal gravity. The results were extensive and in some ways surprising. Scott's gene expression changed measurably during the mission. His telomeres, the protective caps on the ends of chromosomes that are associated with aging, temporarily lengthened in space, which was unexpected. His gut microbiome changed. His cognitive performance shifted in ways that took time to normalize after return. His vision changed, a result of the fluid shift that occurs in microgravity, causing increased pressure on the optic nerve, a finding that has become one of the more significant health concerns of long-duration spaceflight research. All of these findings are not cautionary tales so much as they are maps, knowledge of what happens so that the next generation of spacecraft and missions and medical protocols can be designed around the reality of what the body does in space. The one-year mission was expensive and demanding and produced data that will benefit astronauts for generations. Peggy Whitson held the American record for cumulative time in space for years, having spent over 665 days in orbit across 3 missions. Oleg Kononenko of Russia holds the world record for total time in space, having accumulated more than a year aboard the station across multiple missions. Each of these records represents months of someone's life spent in a place that most human beings will never visit, doing work that most of them will never fully understand, making possible things that all of them will eventually benefit from. The view of Earth from the station has changed people in ways that are difficult to articulate. There is a concept that has been described by astronauts and researchers who study the psychology of spaceflight. It is sometimes called the overview effect. It refers to a cognitive and emotional shift that many astronauts experience when they look at the Earth from space. Not just noticing that the Earth looks beautiful, which it does, but something more fundamental, a shift in the way the Earth feels to them, in the way their relationship to it changes. From the ground, you live inside the world. The sky is above you, the horizon is around you, and the planet is simply where you are. It is not an object you observe. It is the context of your entire existence. You cannot see it from the outside because you are on the inside of it. From 400 kilometers up, everything changes. The Earth becomes an object. You can see it from the outside as a sphere, and you can see all of it at once. The whole blue and white and brown surface of it turning slowly in the black. And something about seeing the wholeness of it does something to people. Astronauts describe losing their sense of national boundaries. From the station, there are no borders visible. The lines that divide countries from each other, that have been the source of so much conflict and so much suffering throughout human history, do not exist in any physical sense. They are agreements or disagreements, arrangements that human beings have made about how to divide the surface of a planet that is, from this height, visibly undivided, a single continuous place. They describe a feeling of protectiveness toward the planet, a visceral sense that the thin blue atmosphere is fragile and important and worth caring for. That the planet is, from this vantage point, obviously finite and obviously alive and obviously the only home available to the creatures that built this station and sent it up here to look back down. Many astronauts have said that returning from the station changed how they live, how they vote, what they care about, what seems important and what seems trivial. Not all of them, not always in the same ways, but enough of them and with enough consistency and sincerity that the overview effect has been taken seriously as a real psychological phenomenon, not a cliché or a public relations talking point. The station is, among many other things, a machine for producing that effect, for bringing people from many nations and many walks of life to the place where the Earth can be seen from the outside, and for sending them back down changed, carrying something that is very hard to describe but impossible to unknow. The station's toilet is a marvel of engineering that no one talks about. There are some aspects of life on the International Space Station that tend to get left out of the inspiring documentaries and the official press releases. Not because they are secrets, but because they are not the kinds of things that naturally come up in speeches about the triumph of human ingenuity. The toilet is one of those things. On Earth, a toilet works through gravity. Waste falls, water washes it away, and the whole process relies entirely on the fact that things on Earth tend to move downward. In microgravity, none of this works. Waste does not fall. Water does not flow. Without some alternative mechanism, what happens next would be not only unpleasant, but genuinely dangerous to the health of the crew and the cleanliness of the station's air supply. The solution is a toilet that works through airflow rather than water flow. A powerful suction system draws air past the user in a controlled direction, carrying waste away and into collection containers in much the way a vacuum cleaner operates, though with rather more precision required. Solid waste is collected into bags that are then sealed and eventually disposed of by loading them into cargo spacecraft that burn up on re-entry, incinerating their contents. Liquid waste, as mentioned in the discussion of water recycling, is processed and eventually returned to the station's water supply. Learning to use this system is, by all accounts, one of the adjustments of early spaceflight life that requires the most specific instruction and the most careful practice before launch. There are training devices on the ground that familiarize crews with the geometry and the procedure. The tolerance for error is minimal. The consequences of inaccuracy in a sealed spacecraft are not abstract. The toilet has been upgraded and improved multiple times over the course of the station's operation, and the latest versions are considerably more effective and easier to use than the original equipment. One of the improvements specifically targeted the challenge faced by female crew members who had historically found the original design less well suited to their anatomy. The redesigned system addressed this more thoughtfully, an example of the incremental, practical engineering work that goes on continuously to make the station a better place to live. It is not glamorous, but it is necessary. And in the history of human spaceflight, the people who solved the toilet problem solved a problem that will need to be solved again on every future spacecraft and habitat and Mars colony and beyond. They deserve, perhaps, a moment of quiet recognition. The station crosses the terminator line between day and night on Earth in real time, one of the most hypnotic things to watch from the Cupola, or in time-lapse photography taken from the station, is the passage of the terminator. The terminator is the line on the Earth's surface that separates the day side from the night side, the moving boundary of shadow that sweeps across the planet as the Earth rotates and as the station moves in its orbit. From the station, the terminator is not a sharp line, but a gradient. As the station approaches it on the day side, the landscape below begins to pass into a lower and lower sun angle, the shadows growing long, the light changing from the white brilliance of midday to the gold and orange of late afternoon, to the deep red of a horizon that stretches for thousands of kilometers. Then, quite quickly, the lit portion of Earth below contracts and fades, and the station is crossing into the shadow, and the night side of the planet opens up below. In the dark, the cities appear. From space, cities at night are extraordinary. Each major metropolitan area glows with a particular character. Some are grids of light, precise and regular. Some spread organically along coastlines and river systems, their shapes revealing the geography that encouraged their growth. Some are isolated bright points in vast dark regions. Some connect to other cities in networks of light that follow the roads and rail lines linking them, threads of luminescence across the dark continent below. The Nile Delta is one of the most recognizable features of Earth at night. The bright bloom of Cairo and the Nile's delta spreading into the Mediterranean, surrounded by the darkness of the desert on all sides. Europe at night is almost uniformly bright across its middle latitudes, a sheet of light with almost no dark patches. The eastern seaboard of the United States is a continuous belt of glow from Boston to Miami. And then there are places where the darkness is nearly complete, where you look down and see almost nothing, and those absences tell their own stories about where people do not live and why. The station passes through one of these day-night transitions every 45 minutes, day to night, night to day, in continuous rotation around the planet. The crew does not experience this as the dramatic event it appears to be in photographs, because they are living on the station's own artificial day-night cycle. But the view through the windows, at any moment, might be midday or midnight below, and both have their own particular beauty. The station is often thought of as a place of technology, and it is, but it is also a place of observation, of watching, of paying attention to a planet that is endlessly various and endlessly interesting, even from 400 kilometers above it, especially from 400 kilometers above it. The station's modules have distinct personalities that astronauts notice over time. The International Space Station is not a single uniform space. It is a collection of modules from different nations, built at different times, fitted with different equipment, smelling slightly differently, lit slightly differently, and carrying the accumulated marks of years of habitation. And over time, the crew develops a sense of each module as a place with its own character. The Japanese Kibo laboratory is one of the largest single modules on the station and has a particular importance in the Japanese space program. It has its own small airlock, separate from the main station airlock, which allows experiments to be exposed directly to the space environment without requiring a full spacewalk. Small satellites have been deployed from Kibo's airlock, floating out into orbit from the end of the laboratory, like seeds released from a plant, each one carrying its own experiments or communications technology. The module has a brightness to it, a sense of careful maintenance that astronauts frequently comment on. The European Columbus laboratory is compact and efficient, packed with experiment racks along every wall, an impression of density and purpose. European astronauts who have worked in Columbus describe a particular pride in the module, a sense that it represents an enormous effort by many countries and many engineers over many years, and that the work done there carries the weight of that investment. The older Russian modules have a different feel. They are cluttered with equipment and cables in a way that can seem overwhelming at first, but astronauts who spend time there come to understand that the apparent disorder is actually a kind of dense practicality. Everything close to hand, everything within reach. The Zvezda service module, which is the core of the Russian segment, was the first habitable module on the station and carries the age of that role. Worn and comfortable in the way that the oldest and most used room of any house becomes worn and comfortable. The nodes, the connecting modules that link all the other segments together, have a character of their own simply because of the traffic that passes through them. Every trip from one part of the station to another passes through a node, and over time these spaces accumulate the sense of being crossroads, places where the different parts of the station meet and where the crew passes each other going from one task to another. Living in a place changes you, and a place that is lived in changes too. The International Space Station has been lived in continuously for more than 2 decades, and in that time it has acquired, in ways that are difficult to measure but easy to feel in the accounts of the people who have been there, something like a character of its own. The station has taught humanity what it actually takes to live in space. Before the International Space Station, human knowledge of long-duration spaceflight was theoretical in many ways, or built from shorter missions and earlier stations that were far more limited in scope. The Soviet Mir station gave some indication, and the American Skylab program contributed early data. But the scale and the continuity and the international scope of the International Space Station have produced a depth of understanding about long-duration spaceflight that simply did not exist before it. We now know, in considerable detail, what happens to the human spine when it is freed from gravity for 6 months. We know how bone density responds and what exercise protocols are most effective at slowing the loss. We know how vision changes and what structural changes occur in the fluid dynamics of the eye. We know how sleep changes in orbit, how circadian rhythms are disrupted by the absence of a natural day and night cycle, and what helps and what does not help in managing that disruption. We know how the immune system behaves differently in space, how certain bacteria become more resilient in microgravity, how the skin changes, how the cardiovascular system adapts. We know what astronauts need in terms of food and nutrition for a long mission, not just calories, but specific vitamins and minerals whose supply or absorption changes in space. We know what psychological challenges are most common in isolated, confined environments, how crew dynamics develop over time, what communication patterns between crew and ground become strained, and why, and what kinds of support are most effective. We know how to build systems that keep people alive for years in a sealed environment, how to recycle air and water, how to manage fire and contamination and equipment failure in a place where you cannot simply open a door and go outside. We know how to plan and execute spacewalks with a high degree of safety. We know how to train crews for every foreseeable scenario and many unforeseeable ones. All of this knowledge came from the station, from the people who lived there, and the instruments that measured them, and the researchers on the ground who analyzed the results. From decades of careful, accumulated, sometimes tedious, sometimes extraordinary, always necessary work. This knowledge is not abstract. It is the foundation on which any future human spaceflight beyond low Earth orbit will be built. Every person who will someday walk on Mars, every crew that will one day travel outward into the solar system in a spacecraft that keeps them alive for years, will do so in a vehicle and with protocols and with medical understanding that was built piece by piece on the platform of the International Space Station. The station is not just a destination or a symbol, it is a school, and the lessons it has taught will be carried forward long after the station itself has come to rest at the bottom of the South Pacific. The station has been a symbol of what is possible between nations. This is perhaps the most difficult thing to quantify about the International Space Station, and also, in many ways, the most important. It is the fact of what it represents beyond its engineering and its science. The station was built at a time when the relationship between the United States and Russia was emerging from the deep chill of the Cold War, but still uncertain, still prone to difficulty. Building something together, something that both countries needed and that neither could complete alone, created a relationship of interdependence that survived political tensions on the ground that were sometimes severe. During periods when relations between the two governments were strained, the cooperation at the station continued, the missions continued, the joint training continued. The cosmonauts and astronauts continued to fly together on the same spacecraft, to depend on one another for their lives. There is a long tradition in human affairs of people who would otherwise be in conflict, finding common ground in shared work. The cooperation at the station, maintained over more than 2 decades through all the difficulties that have arisen, is real and meaningful. Whatever its effects on the political relationship between the nations involved, it represents something that should not be underestimated, a proof of concept, evidence that it is possible. The children who watched astronauts and cosmonauts work together on the station, who saw flags of different nations on the patches of the same crew, who saw human beings from different countries sharing meals and sleeping in the same module, and playing music together and looking out the same window at the same Earth, absorbed something from that. Whether they know it or not, whether they could articulate it or not, they grew up in a world where this had happened and was still happening, where cooperation in space was not a dream, but a fact that circled the Earth 16 times a day. Every day, the station makes something impossible look easy. And perhaps that is the deepest thing about it. Not the specific facts and measurements, as wonderful as those are. Not the science, as important as that is. Not even the cooperation, as meaningful as that is. But the simple daily fact of it. The fact that up there, right now, a small group of human beings are living in space. They are waking up and eating breakfast and doing their work and exercising and looking out the window and calling home and going to sleep again. They are living as fully as they can in the most inhospitable environment any human being has ever inhabited, and they make it look, from down here, almost routine, almost ordinary. Like the kind of thing that just happens, like weather or tides or seasons, like something the universe always expected us to do. They are up there tonight, floating in the hum and glow of the station, 400 kilometers above the ground where you are lying right now. The Earth is between you and the stars. The station is between you and the stars. And everything is as it should be. And so, dear listener, our quiet journey to the International Space Station comes gently to a close. We have drifted together through the facts and the feelings of this remarkable place, 400 kilometers above our heads, circling our world in the deep and silent dark. We have talked about the people who live there, and the air they breathe, and the water they drink, and the way they sleep in bags fixed to the walls of small private rooms while the planet turns endlessly below them. We have thought about the view from the cupola, and the smell of space on a returning astronaut's gloves, and the way a guitar sounds when it is played by someone floating above the clouds. We have sat for a moment with the idea that 16 sunrises happen there every day, and that the water the crew drinks today may have been something else entirely yesterday. We have considered the bone-deep strangeness of living in a place where fire forms a sphere and fluids pool in your head and the sun rises in the west. We have thought about the toilet and the robotic arm and the thermal blankets and the carbon dioxide scrubbers and all the quiet, careful, unglamorous engineering that makes the glamorous parts possible. We have walked through the modules in our minds, the Japanese laboratory and the European Columbus, and the older, worn-in Russian segments and the nodes where corridors meet. We have floated through the cupola and watched a sunrise over the Sahara and a storm over the Indian Ocean and the city lights of Asia appearing as the station crossed into darkness. And we have thought about what it means that human beings built this thing together across borders and languages and histories, and have kept it going and kept people living in it for more than 2 decades without a single day's break. And what those people carried home with them when they came back down, the changed perspective, the fragile blue line of the atmosphere, the planet seen from the outside for the first time. There is something deeply comforting about all of this, if you let yourself feel it. Not only the strangeness of it, though that is real, but the fact that human beings, who are capable of so much difficulty and so much smallness, are also capable of building something like this, of agreeing that it is worth building, of keeping it going year after year, sending people up there to live and work and look out the window and take photographs and grow lettuce and play guitar. The station is overhead right now, in all likelihood. As you lie here, wherever you are, on whatever surface you have chosen to rest upon tonight, the International Space Station is probably passing over your part of the world, moving silently and quickly across the sky, its solar panels catching the sunlight, even if the ground below is in shadow. If you could step outside and know where to look, you might see it, a steady, moving point of light, brighter than any star, crossing the sky in about 5 minutes and then gone over the horizon. But you do not need to go outside. You can just close your eyes and imagine it up there. The gentle hum of the systems, the soft glow of the screens, the quiet breathing of the crew in their small private quarters, sleeping in their bags in the dark, dreaming whatever it is people dream when they live among the stars. And somewhere up there, right now, someone is looking out the window. The earth is below them, turning slowly. The stars are above them, steady and far. The station is warm and humming and full of the work of human beings doing what human beings do, even in the strangest of circumstances, living, learning, looking. Let that be the last thought that carries you tonight. Someone looking out a window at a world so beautiful that it changes the people who see it. Let your breath slow. Let the day's weight drift upward and dissolve. Let the hum of the station carry you, and the slow arc of the orbit hold you, and the light of 16 sunrises ease you forward into the soft and quiet dark. Close your eyes, breathe deeply, drift gently into rest. You are still on the ground, but the stars are not far. Good night.